This is the next video on electronic structure and periodic properties. We just finished talking about waves and the difference between standing waves and traveling waves. And now that we know about standing waves, we can talk more about electrons as a wave. So we can describe an electron as a wave. And if we're going to describe a wave, it's easiest to describe it using a mathematical function. Which is, of course, what we've been doing all along. We just didn't need them to draw our picture of the atom. So we can describe a wave using a function, so we call it a wave function. And we use a symbol to represent the wave function, and that symbol looks like this. It looks like a pitchfork, but it is actually the Greek letter psi. So if we wanted to model the wave that we drew on the previous page, something that was a one-dimensional wave like one of these, we might choose to use a sine or a cosine wave, because that's sort of how an easy function to choose to model a wave of that shape. So we might write something like psi of x, x being the horizontal direction that the wave is standing on. We could model it using a sine function, or we could say psi of x is some sort of a cosine function. Those would be appropriate choices for modeling our one-dimensional wave. But an electron is not a one-dimensional object. It exists in three-dimensional space. So an electron is a three-dimensional wave. So we need three variables in our wave function, one for each direction. And you can imagine that as we start to add variables to our wave function, it starts to get quite a bit more complicated. So if we wanted to write a three-variable wave function, we could say psi of x, y, and z, because those are the variables we oftentimes use in calculus. But because electrons are waves that orbit a spherical object, the atom, we usually use radial coordinates to describe it. And the radial coordinates are r, theta, and another Greek letter called phi. And that is officially as far as we are going to go into the topic, because that is a topic for quantum mechanics. So take quantum mechanics to learn more about electrons as wave functions. For now, just be content with the fact that there is an equation to describe every type of electron in an atom. And so what you will learn if you take quantum mechanics is that these wave functions psi will give us information about an electron's position and about an electron's energy. And that's the only part that we're going to care about in general chemistry. So if we take the square of that function, psi squared, that function represents the probability density, the three-dimensional volume where an electron is probably located. As we said in Heisenberg's uncertainty principle, it can be difficult for us to find the exact location of an electron at a particular moment. So we'll just have to settle for the location where it is probably located. So sometimes it's called the probability density, but usually we call it an electron cloud. sort of like a three-dimensional area where we might find it, or in reference to the Bohr model, where they called the path an electron followed an orbit, this three-dimensional area is usually called an orbital. So that's usually how we're going to refer to it from this point on. So quantum mechanics can give us the location of an electron, the orbital, and Schrodinger gave us an equation to help determine the energy of a particular electron. And that equation looks like this. It has a Hamiltonian operator, kind of like a multiplication or a divide sign, multiplied, taken of the wave function, gives us the energy times the wave function. We are not going to be using that function, but that's what it will look like when you make it to higher level chemistry and physics and need to use that. So with this equation, we can calculate the energy of an electron in a particular orbital. And this field of study is called quantum mechanics, because it studied these tiny quantum particles and the mechanics of how they move. So electron energy and electron location, those are the two main takeaways here. By modeling an electron as a wave using a function, we can determine its probable location in an orbital around an atom and its energy. Now that we have a new model for the way the electron looks, we need to update our what does an atom look like captain's log. So these are all the different models of the atoms that we've looked at. We've looked at Dalton's model that was basically just an empty unit for an atom. Thomson's model after we discovered the electron, and Millikan's model once we know about the electron charge. Rutherford's model, which included the nucleus with protons inside of it. Soddy's model, which said that the protons were the defining feature of a particular element, and Chadwick's model with the neutron inside the nucleus with the proton. So now we need to start a new page of the captain's log and update that model of the atom even further. So we'll add an entry for Bohr in 1913, which we had a couple of videos ago. Bohr gave us electron orbits and quantized energy. And when we drew the Bohr model, it looked something like this. There was a positively charged nucleus at the center of the atom containing protons and neutrons. And the electrons lived in orbits that were increasingly far away from the nucleus. These were called orbits, just like the path that the planets followed in space. And that is where the different electrons lived. And we said that as we moved to orbits that were farther and farther from the nucleus, they were higher and higher energy. And so our final stop on what the atom looked like, the most accepted, most recent version is the Schrodinger model. And Schrodinger introduced electrons as wave functions. So basically, what that means is that our most current version of the atom is math. It is an equation. So our model for the atom is some sort of a wave function with 3 variables in it. And that models a 3-dimensional space called an orbital, where the electron lives. So I know it's kind of a disappointing end that the final picture in the captain's log of an atom is not actually a picture. It's just a math equation, but we can make pictures depending on which orbital we're talking about. But there are many different orbitals and there are many different shapes. So that video with the shapes of the orbitals is coming up next.